Well, thank you for inviting me. My talk is not about something so up-to-date as the previous one. It's something much more traditional and conventional within the temporal graph community, even though there is some strange twist. Let me tell you what I'm talking about. So the universe I'm talking about, the computational universe, is one where we have a finite set of computational entities, which we call agents, and they move and operate in a discrete space. And for all practical purposes, the discrete space is just a graph. It's a finite graph with a finite set of nodes and edges, and the edges are labels. And labels can mean many things, but in particular, we associate them with port numbers. And if you look at what a node looks like inside the node, on each incident edge, there is a port, and the port is a number, and the numbers are consecutive without loss of generality, consecutive integers from 1 to the degree of the node. And about the agents, it's the standard things. They are computational entities, so they can compute, they have some memory, and they execute the same protocol with this. And one more thing, they are mobile, so they can move from one node to the next one. And in order to move, the way they move, you go to a port. And in our model, actually, we say that at any point in time, there is only one agent per port at any point in time. So how do these agents behave? Well, they alternate between active and inactive states. In an active state, what they do, they execute the algorithm. So they look at the environment. If they are inside the node, they look at the ports, they look if there is other agents, if they, depending on the model, they might be able to talk to the other agents. And so they perform this finite amount of time in action, which we call an action, and always concluded with the move if they decide to move in that action. Once this action is ended, they become inactive. And again, while they're inactive, they can stay inactive for a certain amount of time, any amount of time, and eventually will become active again. And the decision on when this happens is an adversary, which is, we call it scheduler. Okay, the scheduler means that these decisions differentiate between different types of levels of synchronization of the system. The most popular one is what's called the synchronous system. Some people actually call it also semi-synchronous, in which you do have clock ticks and which divide the time into rounds, and all the agents which are active in a given round, they perform their action and complete it within that round. So for example, here I have a system with 4 agents, and at any point in time, this is inside this round, I have these 4 agents. In this first round, there is only 2 of them which are active, 2 are not. In the next round, they will have, those 2 are active will complete their action. In the next round, a different subset of the agents become active and perform their action. Who decides? Well, which agent becomes active? Well, that's the adversary, the scheduler. And one particular extreme case is what the very popular fully synchronous, and where it's assumed that all the agents are active in every single round. On the opposite horizon, there is the asynchronous. And asynchronous, you have no notion of round. In any agent, the activity of any agent, and the duration, is totally independent of all the other agents. And again, who decides how long and when? Well, that's again is the adversary. So now one thing is the adversary. The only limits that we have, both in the synchronous and the asynchronous, is a fairness. And I'll come back to this later for a second. So the problem I'm interested in to talk is about exploration. Exploration is the classical problem where every node of this discrete space, or this graph, must be visited by at least one agent. This can be done a finite number of times, in which case we call exploration with termination. or an infinite number of times. We call it perpetual exploration. And this is related to all kinds of other problems. For example, the search. The agents have to find something inside the network, or they have to patrol the network, or they have to construct a map of the network, or have to verify whether the map that they have is accurate. And it's a very long-standing problem. I mean, it was first actually introduced by Claude Shannon. And for those who might not know, he is actually the father of digital logic design and of information theories. And with two papers, one was actually his master thesis, and the other one was his PhD thesis. From such glorious beginning, this problem has become a central problem in theoretical computer science. And it's been heavily studied. And there is lots and lots of work on it. I would refer, actually, there is a recent survey in a chapter in the book on distributed computing for global entities. Now, all this work has been done, especially in distributed computing, within static graphs. Now, what we are interested in is when the graph is dynamic. And the dynamic here, it refers only to the changes in topology over time. So, the graph at some point will just change in time. One way we model this is, there are many ways of doing it. One is of a time-varying graph, which in the most simplified version, essentially is like you do have the nodes and the edges, you do have the graph, plus you have the lifetime of the system, which could be finite or could be infinite. And you have what's called the edge presence function, which tells you if a given edge is present at a given time or not. I mean, the more extended definition of time-varying graphs also include the node presence function and other things. This is sufficient for this talk. Terminology is the usual one. So the snapshot is essentially the graph formed by the edges which are present at a given time, and the footprint is the aggregate of all the snapshots. Okay. Now we have agents that have to move. But now, suddenly, I mean, if you have an edge, the agent can move. But if there is not an edge, what do you do? Well, what do you do? Essentially, you stop your action. You become inactive. And one more thing, if you're inactive and the port is up and the link comes up, you just don't move. You only move if you are both active and the edge is there. Okay, so there is lots of work being done on exploration of evolving graph, of temporal graphs and evolving graphs, and there is actually it's not exhaustive by any means, but there is a recent survey. It's one chapter, a different chapter in the same book. It is actually not only on exploration, but includes also exploration. I have to say that the work that is done is, a large part of it is actually assumes a finite lifetime and is centralized. I'm actually interested in infinite lifetime and distributed, what we call a live exploration. And in particular, I'm interested in deterministic solutions. So, in the rest of the talk, that's what I will refer to. So, the existing work makes some assumptions. And they make assumptions either on the topology of the footprint or on the topological changes on the time synchronization. On the footprint, the typical assumption is well, it's a special graph. A very popular one is the ring, other ones are cactus and others. In terms of the topological changes, one important assumption is what is called temporal connectivity. Temporal connectivity just means that at any point in time, from any edge, from any node, there is a temporal walk. That means there is a way of getting from one node to any other node over time. Notice that this does not imply anything about the physical connectivity of the network. In fact, all the snapshots could be disconnected. I should also stress that this is the weakest assumption possible for exploration. Without this assumption, exploration is impossible. Actually, without this assumption, any non-trivial problem is impossible. There are other stronger assumptions, typically on the physical connectivity, like they run from recurrent connectivity, which means once in a while disconnected, to always connected. And if we look at the Venn diagrams of all these conditions, going all from temporal connectivity to always connected, we have to think that exploration is possible only within this range. I would like to point out and to stress that the large majority of work has been done here in this assumption. Okay, so class 1 is about time and synchronization type of assumptions. Let me say something that, people that be working on time-varying graphs and on dynamic graphs, actually, there's the large portion is totally outside of computer science and engineering. These are people who work, using tools from complex system analysis, and they're mostly physicists. And they look at the evolution of the change over time. Even if the system is discrete, the evolution over time of the system is seen as a continuous process. What we are interested in instead is in a discrete system. What do we mean by discrete? Well, what we mean by discrete is that if we look at the moments where a topological change occurs, so these are all the topological changes. If you take any interval of time, in this case t prime, double prime, the number of topological changes that occur in that interval is finite. Now, why is that important? Well, or relevant? Well, one reason is because then, in this case, what we can do, we can linearize, we can enumerate the times where the topological event occurs, which means that the time-varying graphs can be uniquely represented as the sequence of the snapshot in those moments. Now, this is, what we would call an evolving graph, temporal graph. However, I mean, this term, when people use this term, they mean something, even not just discrete system, they mean something else. They mean something which is not only discrete system, but also the time is discrete. The time is discrete, so the time is positive integers. What does it mean is that, there is a clock, and the topological event changes occur precisely on some of these clock tick points. And obviously, the snapshot, stays the same. The graph stays the same until the next change. Let me just point out that discrete system does not imply discrete time. Okay. Stronger assumption is when not only you have discrete time, but you have the synchronous the system you say is synchronous. What does it mean? It means that any action of this, anything that happens within one time unit or within one round. And even stronger is a fully synchronous system when not only synchronous, but everybody, all the agents are active at the same time. So if we look again at the Venn diagram of these things, we are only interested in the discrete sides, for the moment, and I would say that the majority of the work is down here, and this is what I would call is the asynchronous, is where you don't make this about the rest. So, what are the minimal assumptions for exploration of some temporal graph? Well, if we look at the topology of the footprint, obviously we don't want to make any assumption. So it's arbitrary unknown. On the topological changes, the minimal and necessary one is the temporally connected. And for time synchronization, we want asynchronous. Now, when we deal with the synchronicity, now what we have to do, we have to deal with this scheduler, which is, is the one who decides when somebody is active, who is active, for how long is action, but makes all the decisions about the changes in the topology. I mean, this is what we call the passive, obviously, dynamic system. And so we have a very powerful adversary. As I mentioned, the only and minimal assumptions that we make is the fact that it's fair. What we mean by fair, it means not only that every agent is activated infinitely often, and here we mean in a strong sense, but at any point in time there exists one other time where this success time when this occurs. But it's a more general thing. It says that even not only you're activated, but when you're activated, if you require a condition in order to act, to do things, and this condition is enabled infinitely often, there must be at least one time where you are awake and the condition is enabled. So it cannot prevent you forever from performing something if there are possibilities. So this is the basic. So this means, for example, that if I'm if I'm on a port, and eventually I will be awake when the link will come up, if the link is infinitely often available. Okay. So now exploration of asynchronous temporal graphs. There is a paper, some results we've done with my co-authors Goto, Flocchini, and Masuzza on perpetual exploration. And this one has many good features in the sense that it uses the minimal things about assumptions, except for one, which is semi-synchronous. Now, and it does actually, as there is in particular one result, this I'm talking about, which does it for anonymous agent, anonymous network, and the optimal number of agents. And the interesting thing is that actually it's possible to modify the protocol so that it does work really in asynchronous. So actually it's possible to do the exploration with the minimal number of things and with the optimal number of agents. Let me, in order to explain very briefly, what is the result, let me introduce. Yes.
Two more minutes.
Fine.
Okay.
An agent is said to be recurrent if it appears infinitely often. And the measure that we use for a graph is the solidity, is the number of recurrent edges. And the key point is that this is the key parameter to tell us if exploration is possible. In fact, if you have only two times the evanescence of a temporal graph agents, you cannot explore the graph. There are some graphs that cannot be explored, even if it's fully synchronous. And this is the type, you have infinite classes. On the other hand, they are, if you have one extra agent, then you can do it. And the mechanism we use is an extremely simple algorithm, which is a modification of the classical rotor, which is a collective rotor, but essentially you just go around with the marker and you just go around trying to find an empty place. And if you find it, that's where you go. Otherwise, you continue and until you. And if you don't find anything, well, you return and wait. And that's it. These two results, this very simple protocol works, and works asynchronous and gives out the bounds for asynchronous exploration. So we can do perpetual exploration with the minimal assumptions, but actually what happens, these assumptions are actually the minimal assumptions for any computation. So, and the difficult part is this one, the asynchronous one. It is totally unknown how to do these things. And in fact, the entire purpose of this talk is to invite people to study this more general class of temporal graphs. Thank you.